So today we'll be solving one new problem which has been asked in Google in VMware. So the problem is popularly known as maximum index. Okay, wherein suppose you are given an array which is suppose 7, 2, 3, 81, 23, 35. Okay, so you have to find a pair of indices I comma j such that array, this is your array of I is less than equal to array of j. Okay, so there may exist multiple such pairs. Okay, you have to find such a pair such that j minus I is maximum among all these pairs. Okay, and this maximum should be our output. Okay, so for example, what we'll do, let us try the very naive approach. So I is 7 and j is 2. J is pointing to 2. So I is here, j is, this is I and this is j. Okay, so this condition is satisfied? No. Then we will move this pointer one more. This condition is satisfied? No. Move this pointer one more. This condition is satisfied? This condition is satisfied? Yes. What is the difference between this and this? It is, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5. The difference is 3. So thus far our answer is 3. Okay, then again we push this one. Okay, this is greater, so 4 minus 0, so this 7 is less than, so this condition is satisfied. Condition number 1. Okay, so this is the only condition. Okay, this condition is satisfied. So now our answer will be updated to max of 3 comma 4 minus 0, which is 4. Okay, then if I again increment this one, so this condition is satisfied, then 5. Now this, for this array, this is the maximum possible value. Means minimum can be, means error of I, some element will be small here and some element will be large here. So for any array of n elements, so the best maximum possible answer is n only, n minus 1, sorry, n minus 1. Difference between j and I. Okay, so for this also this. So but suppose this was not 5, this was 3. Okay, so in that case the answer would have remained 4 thus far. Then for next iteration we could have checked this one. We could have we will increment I. So in this way we are actually checking all the pairs. So how we are doing it is that for, so we are initializing I equal to 0 and j equal to 0. Okay, so this is the naive approach. Okay, then this is not for. Okay, now I is equal to 0, j equal to 0. Now we will loop over, with I we will loop over the elements as a reference element as this I, and with j we will recursively, means in inner loop we will loop over the next elements. Okay, and we will have an answer is equal to 0, because by default the answer will be 0 only. Okay, if all their elements are same, suppose all are 7 7, so everyone satisfied this condition. No, actually if the array is in descending order, okay, then none of the these things will satisfy this condition, but only for all this condition will be satisfied only when I equal to j. In the descending condition, like suppose the answer is, the array is 80. Okay, the array is 80, 70, 60, 50. Then for in, there does not exist any I such that error of I is less than or equal to error of j, such that I and j are distinct. Okay, so for this only, for I equal to j only, this condition will true. So in that case the answer will be 0. Okay, that is how you're initializing it to 0. Okay, then we have to check. We will have to while I is less than n, n is the size of the array. Okay, then inner loop while j is less than n, will modify j equal to I plus 1. Okay, in this we'll check if array of I is less than equal to array of j. If this is the case, then answer is equal to max of arr of, sorry, max of a and s comma j minus I. Okay, so in this way we will add, finally in our function we will return answer. Okay, so this, what is the time complexity of this approach? Okay, we are not incrementing I here, so I'll increment j here. There is one incrementing, so this line will contain j equal to j plus 1, and finally before this, so because of space and problem of space in the screen, I'm facing some trouble here. Okay, so this is the code snippet. Okay, and so we'll try to analyze this is the same code as I written above, so in a more elegant manner written in uh, using keyboard. Okay, so what is the time complexity of this one? So there are two loops. One is this, and another is, oh, this color is really cool. Okay, so this loop will run how many times? So, and this loop will run n times given the length of the array is n. Okay, so this loop will run for the first time, it will run n minus 1 times. Okay, then for the next time it will run n minus 2 times. As you can see that when I is equal to 0, okay, when I is equal to 0, it is going from j equal to 1 to n minus 1. When I is equal to 1, it is going from j equal to 2 to n minus 1. Okay, so on and so forth, I n minus 3, so on and so forth up till this will run only once. So if we sum this up, if we sum n 1 plus 2 plus 3 up till plus n minus 3 plus n minus 2 plus n minus 1. So basically I've just reversed this. This 1 comes here, this 2 which is represented by a dot comes here, and so on and so forth, and this n minus 3, this is n minus 2, this is n minus 1. So if we sum this is the sum of n natural numbers, sum of n minus 1 natural numbers. So it is n into n plus 1 by 2. Okay, so just in the original formula I have replaced n with n minus 1, and we get this. Okay, so when we open this equation, then this becomes n square minus n by 2 by 2. So this is effectively O of n square algorithm in terms of time complexity. Okay, now we have ignored this term, this linear term. We have put this quadratic term in this because it is a higher order term. Okay, now what is the space complexity? So have I used an extra space? Yes, I have used 3 extra spaces, but is it related to the input size? Means if the array size is 100, if the array size is 1000 or 10,000. Okay, so will it grow? No, will ultimately be using only 3 variables. So space complexity is O of 1. Now we want to improve this time complexity. This is a quadratic time complexity, so it is a huge time taking process. In computer science, we always try to optimize. So how do we optimize this one? So how do we optimize this? Our original time complexity was O of n square, order of n square, and space complexity was order of 1. Okay, so how do we optimize this one? So you see, just one some intuition that I'll try to give here is that suppose the pair that we are talking about, ARR of I and ARR of j, means we have to find such pairs such that ARR of I is less than equal to ARR of j, and we have to so if the number suppose is 3, okay, so and we are talking about suppose this pair, so obviously this pair satisfies this criteria, and the difference between index is this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, 7 and 8. Okay, so 3 minus 1 is 2, so the difference is 2. But as long as we have a greater element to the right side of this element, so this doesn't matter. So instead of 8, if we select 9, so our answer will be incremented by 1. 4 minus 1 is 3. Instead of this, if I select 10, then it will become 4. 5 minus 1, 4. In the same manner, if we have this 10 as one of the is as one element of the pair I comma j, ARR of I comma j, and we have this 9, so the difference is 1, j minus I is 1. Now we can try to push this pair to the leftmost side so that we can land upon a element which is less than this, and if we do this, then we will be able to maximize our j minus I value. Means j minus I will be maximum if we have this I towards as leftmost as possible and this j towards as rightmost as possible. Okay, so we will, so using this idea we will have for this we will have an array, auxiliary array, which we called as min. Okay, or we can say, okay, left min. Okay, and this will actually store this the ith element, of this array will actually store the smallest element up till the ith index from the left hand side. Similarly, for this one we have error of j, so r min of j, which will store the smallest element up till the jth index, sorry, this is not the smallest, this is the largest index from the right hand side. Okay, so if we go about forming such an array, okay, so this is what we have. So given this array, okay, with our original array which is the ARR, okay, we will have the L min as this one and R min as this one. So you see how we form this. So this is 7. So by default, from the left, including this one, the smallest element is 7. Now when we reach this, then from the left, including this one, the smallest element is 3 in this subarray. Okay, in this subarray. Okay. Then if we see this, then from the left, including this element, means in this subarray 0 to 2, the smallest element is 1. Okay, and from the left, including this element, the smallest element is 1 in this subarray 0 to 3. Similarly, in the 0 to 4 subarray, we have the smallest element as 1. In 0 to 5, if the smallest element is 1, 1, 1, 1. So we are done. Okay, so for our min, will go from the right hand side. Now, the largest element to the right, including this element, is 6. Now, the largest element to the right means in this subarray, 7 to 8 subarray, it is 6. the largest element to the right, including this element, means 6 to 8 subarray, it is 6 is okay. And similarly for this one, small largest element to the right, including this element, is 10. And since 10 is the maximum value, so we will so if we go to the leftwards more, so 10 will be only replicated because it's the largest element from any index after the, including this and after this, till the last element. Now how are we going to exploit these things, these two auxiliary arrays? And you understood, I hope you understood the intuition is that we have this j, so we want to push I to the leftmost and j to the rightmost, because if we have 9 here, we have 10 here, we have a got a pair, but and this 9 is less than equal to 10. Okay, we are satisfying this condition. But if we have 1 here, as long as we have 1 here, we don't care about 9, because ultimately this 1 and this 10 will give us the largest. And if we land on this one, and we take into account, suppose we are on 1. Okay, oh, okay, we are on 1 and we are accounting for this pair. Okay, so we are on 1 and we are accounting for this pair. This difference will be 2. Okay, 2. But we can increase this difference as long as we have an element that is greater than 1 and to the right side of this array. So this 6, we can use this, so then our difference will increase. Okay, so that is why we have this auxiliary as that is keeping the smallest element from the left up till up till that element, and this r min, which is keeping the largest element from the right up till that element. Okay, now how are you going to utilize this one? So we have an I here, we have an I here and a j here. Okay, now these are elements, so these are not indices. This is the index, these are the elements, 7 and 10 are the elements. Now is I less than equal to j, is means we will go through the indexes of this array. Is L min of, is L min of I less than equal to R min of j? Okay, is it true? Yes, then we will update our answer. Okay, so the answer will be ans is equal to max of ans, as we had previously, ans. So so this is maximum of answer comma j minus I. Okay, so now j and I are both same, so this answer will be 0 only, so this will not be updated. Now we will increase j as long as this L min is less than equal to R min is satisfied. Okay, so this will be satisfied up till this one. Okay, so and all along we will actually updating this. So when j and I are same, if they are 0, then answer is 0. Okay, so now I will increment j equal to j plus 1. Okay, so j will come this side. Okay, now j will come this side, then j minus I is 1, so the answer will be 1. This condition is satisfied. So then j minus I is 2, answer will be 2, 3, 4, then last we will have 5. Now at this point, when we increment j, this will become 6. So this condition is not satisfied. So then we will increment I. Okay, we'll increment I, and then again we'll check the condition. If this condition is satisfied, then we will update our answer, we will increment j. Else, we will increment I. Okay, if this condition is satisfied, then we'll update our answer and we'll increment j. Else, we will increment I only and will not be updating our answer. So you can see in this array, every time we are, like in this phenomena, we are looking towards the smallest element from the left end and the largest element from the right end. So in this manner, we are able to capture the answer for this one without going for a tedious approach, which was a naive approach of n square time complexity. So I'll write the code. So I'll be writing the code using the whatever we have done. So min will have L min and R max as our lists. Okay, and Firstly, we have to create this array. Now this array, how will be creating? We have to store. So this will store minimum from the left. Okay. So how do we do that? So first we will have l min will initialize it with l min dot append. So okay. So the sizes of this l min and r min will be the length of the array. Okay, so we can do like this, that is not a problem. And l min, we will initialize the 0th index with the ARR of 0. Okay, because to the left we have the smallest element, you including this one is 7 only. Okay, and then we will traverse through our array for I in ARR. Okay, not so we need the index, so I equal to 0. Okay, I equal to 1, so I equal to 1, then while I is less than n. Okay, while I is less than n, so what we'll do is that l min of I is equal to l min of I minus 1 comma ARR of I, minimum of both this. Okay, so that means what? Initially we started with 7 and then we move our index to 1, and we have to increment I also. I plus equal to 1. Okay, and we'll check up till this. So this 3 comes in, and including the array, and then we will actually update our lmin. So this is how lmin is made up. Similarly, we have the rmin. So rmin will have r max, we will actually update from the right hand side. Okay, we'll actually fill in from the right hand. So this initial value will be equal to n minus 1. How? Because what is rmin storing? Rmin is storing the maximum element from the right hand side of the array up till that index. So this index is 8. So up till this index, the maximum element including this to the right hand side is 6 only, because there is no element. For this example also, for 7 to 8, the maximum value from the right hand side up till this is 6 only. So this is how this is populated. Okay, so then we will again we will actually I equal to 1 as a not 1, I is equal to n minus 2, then while I is greater than equal to 0. Okay, then r max of I equal to max of r max of I plus 1, means whatever we have thus far, and ARR of I. Okay, and I minus equal to 1. So in this way we'll have r min and l min and r max. Okay, now we have to utilize this l min and r max. So how are we going to do this? We'll have answer equal to 0, which is our default answer, and we also have I comma j equal to 0 comma 0 comma 0. So I is for l min and j is for r max. Okay, then we will actually iterate as long as I is less than n and j is less than n. Okay, now if l min of I, if this condition, now we're going to fill this condition, l min of I is less than equal to r max of j, then what we'll do, we will update our answer equal to max of answer j minus I. Okay, and we'll also increment j, because we want to push our boundary and we want to see whether there is more possibility or not to expand this j minus I. Okay, and if this is not the case, then we will actually increment I. Okay, and then we'll return our answer. So let us see if this compiles and this works. So yes, for this one we are getting the answer. So let us see if this can be submitted. So 1114 test cases, too much. That is why it is taking some time. So yes, so it is working. Okay, so that is how we are doing. So we have, so what is the time complexity of this program? So this is, you can see, this is a linear loop. This loop is linear. So this loop is actually running in O of n time complexity, and this loop is also running in O of n time complexity. Okay, so there is no double loop, single loop, and this is also single loop. So this is running in O of n time complexity. Okay, so in all total we have our time complexity as O of n plus O of n plus O of n, which is equal to O of 3 times n, which is equal to O of n, because we get rid of this constant factor in time complexity. This is order of n. And what is the space complexity? So are we using extra spaces that is actually proportional to the array size? Yes, we are using this L min and R max, which is extra spaces of size n. Okay, so the space complexity is O of n for L min and O of n for R max, which is equal to O of 2n, and because we get rid of this constant term, so this is O of n. So that is how we have effectively come from, we came from O of n square to O of n, but we had to use some space from O of 1 to O of n. So this is why algorithms is a trade-off. So you are optimizing, we were able to optimize the time complexity, but we had to use some extra space. So that's it for today. Thank you guys for joining.